So we'll get started. Welcome, everybody. Thanks for joining this session today on MariaDB and PostgreSQL, technical deep dive comparison. In modern architectures, when teams look at open source relational databases, the conversation almost always comes down to PostgreSQL and MariaDB. Both are powerful engine, both are proven in production, but they take very different routes to get there. When I was compiling this presentation, I was debating how to make a technical deep dive more engaging while not compromising on the content itself. Right. The goal here, or my goal here, is to make the session as engaging and impactful as possible. I'll promise I'll make the best use of the next 45 minutes or so of your time. I also have a lot to cover. So if you do have questions, please ask them in the chat. A quick introduction. I'm Manoj. I lead the database migration practice at MariaDB. My background spans years of building and optimizing large-scale data systems across both enterprise databases and open source platforms, including my time at IBM and EDB. These are experiences that have shaped how I think about performance, scalability, and design trade-offs when you use various databases. On the agenda today, it's a deep dive to understand how each of these engines are built, why they behave differently under load, and where each one shines. We'll walk through the engine internals, look at how they handle concurrency and indexing, explore their MVCC implementation and housekeeping behaviors, and then move into replication and high availability, seeing what each does natively and what is enabled by the ecosystem. And finally, we'll get into connection, pooling, load balancing, where we look at tools like PG Bouncer, PG Pool on the Postgres side, and MaxScale on the MariaDB side. By the end of the session, the idea is simple. You should walk away with a clear picture of the architectural DNAs of both databases by understanding how each engine works under the hood and what design trade-offs each of them make to accomplish the database tasks. Let's start off with the database architecture. Okay, this slide gives us a general representation of the PostgreSQL architecture. At the core, PostgreSQL follows a multi-process design. Every client connection is handled by its own backend process, managed by what is called the postmaster daemon. At the core, PostgreSQL follows, it offers a strong isolation, and processes don't impact one another, right? But it does mean higher overhead through operating system context switching compared to a thread-based engine. The shared memory area is central to how Postgres works. This includes shared buffers, write-ahead logs, or wall buffers, and various other control structures to keep the data moving efficiently between memory and disk. Each process also has its own local memory for quick access to the working data set. What's different in buffer management is PostgreSQL uses a clock sweep mechanism approach for handling data pages in the buffer. It's basically a lightweight version of the least recently used queue, or the LRU queues that you hear about. Here, the pages are aged out without maintaining a complex algorithm to track the dirty pages. Background or utility processes handle maintenance, consistency, and recovery tasks in the background. Processes like wall writer, checkpointer, background writer, auto vacuum are examples of background processes. On the storage side, PostgreSQL has a single unified storage engine. which is a bit different from MariaDB, where you could pick from multiple storage engines. Um, um, uh, Now, every at the store, every modification is first logged into a WAL file. The WAL records are written sequentially and tracked by LSN, and prevents any other, any out of order events for durability. Right. You'll also notice that there is a mention of extensibility here. That is a huge part of Postgres's appeal. And this makes Postgres into a full-fledged data platform. And this is through an ecosystem of extensions that it provides. In summary, this architecture is solid, traditional, and standards-driven. It's quite robust and stable, though it does carry a heavier footprint. So this leads into one of Postgres's biggest strengths, right? And those are its extensions. Extensions are basically plugins that add new features directly into the database. For example, if you want GIS support, you install GIS plugin. If you want full text search, or new data types or custom indexing methods, there are extensions for that. Now, these extensions feel native. They integrate right into the SQL, so developers can use them as if they were built into the core database. The extensibility is part of why Postgres is become a platform, not just a database. So while extension makes Postgres flexible, they can also introduce other pain points. Upgrades may become challenging. Version mismatch and maintenance overhead would be higher, especially since many extensions aren't well maintained. And have only limited support from selective vendors. You have to do your due diligence before deciding which extensions to use in your database and solution, because there is a risk and the onus of supporting it may fall on the users themselves. Now, let me walk you through MariaDB's InnoDB storage engine and how it's put together, right? One of the first things to understand about MariaDB is that it is built on a pluggable storage engine architecture. This means you can choose the right engine for the job. For example, InnoDB for transactions, column store for analytics, and so on. But for most production use cases, InnoDB is the default because it delivers full ACID transactions while while providing crash safety and high reliability as well. MariaDB uses a threaded architecture, unlike Postgres. It runs background threads. Each of these threads has specific roles, from checkpointing to page cleaner threads for flushing dirty pages, log writer threads to handle redo logging, and bin log threads to name a few of them. This threaded model makes MariaDB lean and efficient, especially in modern multi-core systems. Now, at the memory layer, buffer pool is where data and indexes are cached, and to avoid constant disk access. It uses an LRU list to decide which pages stay in memory, which gets pushed out, and so on. MariaDB tries to serve as much as possible from, directly from memory. Durability is also where InnoDB's strength lies. There are two kinds of log pertaining to this that you'll hear about. One is the redo logs, which belongs to InnoDB. It ensures that the system crashes. If the system crashes, InnoDB can recover from the last committed transaction. The binary log, also known as bin logs, belongs to the MariaDB server itself. It ensures that changes can be replicated to other servers for roll forward during point-in-time recovery. The two work together at commit time, and transactions are written to both. Now, on the disk, right, InnoDB has a couple of more safeguards. the undo logs, which stores the old version of the transactional row. This is what makes rollbacks possible, and also enables MVCC so readers don't block writers. The double write buffers act as a safety net before data pages are written to the main table space. They are written over here. Now that way, even if the system crashes mid-write, you don't end up with half-written or corrupt pages in the database. MariaDB, like I said, is built on a pluggable storage engine architecture. So while Postgres uses a single unified storage model. Now think of these engines as interchangeable parts that you can drop in. Right? InnoDB is your default workhorse. It's great for general purpose apps with mixed reads and writes, and it is the most popular and widely used storage engine. But if you're doing heavy analytics and reporting, you could switch to a column store. It is designed to crunch big data fast. If you need to spread your data across multiple servers, for example, right, you could use Federation for disparate data source, and it also provides, the Spider engine also provides data sharding, which essentially addresses the technology that you need to be able to shard your data across servers. The key takeaway is that you can mix and match these engines with the same database to get the best database engine for the workloads that you may have. Now, on the right-hand side, you'll see information about MariaDB plugins as well. Now, they essentially let us extend the database capabilities beyond the core functionality. Now, this includes really important things like, key management for encryption, right? For example, working with HashiCorp or AWS KMS and so on. Authentication modules like PAM or GSS API. And as you can see, storage engines, even storage engines themselves are managed as plugins. It's also important to note that MariaDB plugins are typically lower-level modules that extend the server's functionality, and therefore they are much more controlled. Postgres extensions, on the other hand, typically extend the data model and SQL capabilities of a database, while MariaDB plugins often extend the server's core infrastructure and behaviors. If I summarize, Postgres is a deeply extensible object-related database. It's a multi-process architecture, delivers reliability while extensions allow for integration of new SQL capabilities. MariaDB, in contrast, is a flexible modular server built for optimized performance and compatibility. Its pluggable storage engine enables fine-grained control of your use of the storage engine. It also lets you mix and match core components to get the best performance for your workload, whether it is transactional or analytical. All right. Let me just quickly check. I hope I'm audible. If somebody could give me a thumbs up and say, it looks good, that would be great. All right. Let's continue to the next section, right? Concurrency control and indexes. Now, as we know, concurrency control is at the core of every database engine. It is the architecture on how the system handles multiple users reading and writing at the same time, while still keeping the data consistent and reliable. Now, the way a database handles this determines its performance and scalability and also operability of the database engine. In the early days of databases, the common method was to use a locking mechanism. It was done by placing locks on rows or pages, depending on the granularity that the transaction demanded. Now, this meant that when one user was writing, others had to wait. Depending on the concurrency levels, even readers might have had to wait, right? This meant that high contention in the database for heavy workloads, and effectively, it's a simple mechanism that avoids extra data versions, but it often slows things down because readers and writers block each other. To solve the locking challenge, database systems adopted what is known as MVCC, or multi-version concurrency control. Now, instead of locking data and data pages, the database saves the old version of the row before creating newer versions of it. This allows readers to get a snapshot of the data as it was, when their transaction started, while writers can keep making changes in parallel to the data and not get blocked, right? Undo segments in database engines are an example of the use of MVCC. Now, does it mean that locking is not required in an MVCC implementation? The answer is no, right? What if there are two writers working on the same row simultaneously? So while MVCC is designed to prevent concurrent read-write conflicts, it doesn't handle concurrent write operations, which are managed by traditional locks. Therefore, these two mechanisms are right in their own ways. Traditional row-level locking is used for update, delete, insert, and explicit locking of reads may also be done. For example, a select for update statement can also lock an explicit read. This prevents two writers from modifying the exact same row simultaneously. All right. So let's now go into the nuts and bolts of this concept, because this is where the crucial differences lie between the two engines, right? Let's take a look at how MVCC is actually implemented in Postgres, and later we'll compare this with how NODB engine in MariaDB does it. As I mentioned earlier, MVCC avoids read-write conflicts by keeping snapshots of the data. Okay, so each database engine does this differently. Now, let's understand this from an orders table, right? So, for example, in the example that's shown here, a user updates order ID 11, depicted by the column OID. At the same time, the user updates, say, order ID 13. This is what we see in step 1. What does Postgres do? It makes a copy of the row in a new slot and applies the update there, leaving the current row with the original value for other readers. Now we have got two versions of that row as shown in step 2. Behind the scenes, Postgres tracks these versions with the hidden system column like xmin and xmax. We won't go into the details here, but essentially note that they mark which transaction created or deleted a version. So Postgres knows which version is the latest. Now, let's say there's another update to order ID 11. Again, Postgres doesn't overwrite the row. It creates yet another new version of the row as shown in step 4. So now we have got 3 versions of order ID 11. The original, the one from the first update, and the one after the second update. Now, when we query for order ID 11, Postgres starts with the oldest version, and it follows the version chain until it gets to the latest one. Now, that way, readers can see a consistent snapshot, while writers can keep safely create new versions without locking each other. Now that we have seen how Postgres creates multiple versions with MVCC, that raises an important question, right? What happens to the indexes when the rows keep getting newer versions and locations? The old version of the row is marked as dead, and the new version is inserted into the table. The new row version gets what Postgres calls a CTID, which is basically a physical address to the table row. Now, when that happens, Postgres creates a new index entry pointing to the new CTID. That's what you see in the diagram. For example, for order 11, you would see that there are 3 versions, all have separate index entries because each version has got its own CTID. It's important to understand that the index itself doesn't store versioning information like xmin and xmax. The index is just a pointer. So when you do an index scan, Postgres will follow the index, hit multiple versions of the same row. It checks the version metadata to decide which one is visible to your transaction. This is done through something that Postgres calls visibility rules. To optimize this, Postgres has also introduced an optimization concept called heap-only tuple updates, or HOT updates. This may improve the operational efficiency. What this means is that Postgres can skip creating new index entries, thereby reducing what's known as index bloat. So essentially, if none of the index columns are changed and space is available in the same page, it can optimize it using heap-only tuple updates. Similarly, secondary index also have to update their mappings to the new physical address as changes happen. All right. Now let's walk through the same example on how multi-version concurrency control actually works inside MariaDB's InnoDB engine, right? And as you'll see from the diagram, the implementations are starkly different. Let's use the same example and start with our orders table. Each row has not just the data columns, but also hidden InnoDB system columns, transaction ID, role pointer, and the row ID. This forms the backbone of the MVCC implementation in MariaDB. Now, imagine a transaction comes in and updates the quantity for the order, say order ID 11, changing it from 5 to 10. Now, this is where step 1 happens. Before making any physical change to the table, the engine first saves the before image to the undo logs. At this point, a rollback pointer is created in the row, pointing to that undo entry. Now, this allows for 2 things, right? It allows transactions to still see the previous version of the data, should it be required. And the second thing it also allows is concurrent readers see a consistent snapshot of the data, even while updates are happening in place. In step 2, the new value quantity of 10 is placed in the redo log buffer, along with its transaction ID and rollback pointer. The redo log is what ensures durability in the case of a crash. We can recover it to a consistent state. Now, when a transaction commits, that's step 4, the changes are written to the binary log. This is the point at which information for replication or point-in-time recovery mechanisms get their record of the change itself, right? Finally, in step 5, background threads like checkpoint process and page cleaners take over. They flush the dirty pages from memory to the actual files on disk, hence making the changes permanent. Now, if you look at the bottom section, the disk view, you'll see that the updated rows have a new transaction ID and rollback, and so does the rollback pointers, right? Rollback pointers have 50 and 51, transaction IDs have 100 and 101. These each link to the active row to its undo log chain so that the engine can reconstruct the older version when it is needed. Once the undo logs are finally purged, the rollback pointer then becomes invalid. Notice that the DB row ID stays constant throughout the update, unless, of course, the update leads to a larger row size that does not fit in the page, right? In which case, it moves the row to a different page and updates our address. So the key difference here in comparison to Postgres that's noteworthy is that MVCC in MariaDB makes the update in place, unlike Postgres where the full row is copied to which the updates are applied. Here's another big difference in how indexing is implemented between the between MariaDB and Postgres. It's a key reason for its performance efficiency here. InnoDB organizes data using a clustered index. Now, what this means is that the table data itself is physically stored in alignment with the primary key. The table ordering itself is a primary key index. The rows live right at the leaf node of that index. Now, if a table doesn't have primary key, InnoDB automatically uses a unique or a not null index, or it creates a hidden DB row ID behind the scenes to keep every row uniquely identified. This is depicted in the diagram over here. All secondary indexes work a bit differently as well. They do not point to the physical location of a row on the disk. Instead, they store the primary key along with the indexed column value, right? Or even the DB row ID, right? If there's no primary key. So fetching a row in a secondary index is a two-step process. InnoDB first finds the key, uses that key to fetch the actual row from the clustered index as shown in the diagram. Now, here's where InnoDB also differs, right? If you update a row but don't change any of the index column, none of the indexes needs to be updated. Only the data changes, so there's no index churn. Another question that may come to mind is the cost of an insert into a clustered table, right? And the answer is it depends. Generally, primary keys are sequential and those do not have an impact on inserts as new ones just append with a new sequential value. But say when a primary key is a random value, for example, a combination of a last name and a date of birth, then there is an overhead to maintaining the clustering, right? So you basically design your database keeping this in mind. In summary, Postgres uses an append-only MVCC that creates a new tuple or a row version for every update. There are exceptions to this rule using the concept called heap-only updates that was described earlier. MariaDB's InnoDB MVCC implementation allows for in-place updates to the row and uses a clustered primary key for physical ordering. That achieves low index churn and minimal insert cost if the primary key is sequential as opposed to a random key. Now, concurrency control maintenance, right? One of the biggest challenges in Postgres comes from how it handles those old row versions created by updates and deletes, right? Over time, these leftover versions called dead tuples start to pile up. This results in table and index bloat, where the storage keeps growing, even though the amount of active data hasn't changed. To deal with that, Postgres relies on a process known as a vacuum process. There are two flavors of this as depicted in the chart. The auto vacuum runs in the background to clean up dead tuples. It doesn't release the space back to the operating system, but allows reuse of the page by the same table. The heavier vacuum full can compact and free that space, but it comes with a cost. Now, in that it is blocking. It's also resource intensive, which makes it hard to run frequently on busy systems. So while vacuum keeps the system healthy, it also adds a maintenance overhead and performance lag for write-heavy workloads. Postgres community is well aware and has acknowledged this as one of the key pain points of its MVCC design. It's something that they continue to work around, but haven't fully eliminated the challenges. Now, in comparison, InnoDB engine is a self-managing and low-maintenance storage engine. It doesn't need manual vacuuming or cleanup cycles, as its MVCC implementation does not introduce bloating. As you know by now, the update and hence the latest version of each row resides in the table, while the older versions are stored in the undo segments. It also stores the differentials instead of full copies of the rows, making updates lighter and faster. InnoDB uses background purge threads that automatically handle housekeeping. These are continuous and efficient and does not require any user intervention. Because of this design, a storage engine remains bloat-free, even under heavy update workloads. It also uses a 64-bit transaction ID, eliminating any risk of transaction wraparound, something that Postgres still manages carefully. So overall, this implementation of MVCC delivers the same concurrency and consistency, but with near zero maintenance. It's a truly hands-free storage engine that keeps itself clean. To summarize, both Postgres and MariaDB are using MVCC to let readers and writers read data at the same time without blocking each other. It's a great way to handle traffic. The main difference lies in its implementation and its impact on ongoing transactions. Postgres is a little bit more manual, creating a full copy of the row with every change, and it needs a separate vacuum process to clean up. The benefit to this is that the old version of the row is readily available, unlike in MariaDB where it has to be constructed from the undo segments. Administratively, MariaDB is generally more hands-off. With the latest row version in the main table and the previous version in the undo logs. Cleanups are much lighter and simple and managed through the built-in purge thread as well. It's a key distinction in the overall design implementation between these two databases. All right. I hope you're following along. I don't have much from a feedback perspective. There is one Q&A. Let me quickly let me see if I can answer that. You said Maria plugins are not meant to extend SQL capability in the data. However, there aren't any new types added to MariaDB as plugins. No, I think MariaDB extensions can also add SQL capabilities, but they are primarily more ingrained into the core database engine, right? So unlike Postgres, where anybody can create an extension, these extensions, the plugins in MariaDB are more controlled so that it doesn't impact the core functionality of the engine. Sure. I think this is a recorded event, so we will share the recording subsequently. All right. Thank you. Thank you for that feedback. I'll continue down this path, right? We still have a few important topics to cover. Replication and high availability is a fundamental concept that is expected out of every database engine. So let's see how MariaDB and Postgres implements them. Postgres implements streaming replication to maintain near real-time synchronization between a primary and one or more standby servers. All database modifications in PostgreSQL are first captured in the write-ahead log, where a sequential record of every transaction is maintained. The log is the single source of truth for both durability and replication. The wall sender process on the primary continuously streams wall records over a persistent TCP connection to the wall receiver process on the standby. This is represented by steps 2 and 3 in the chart here. The standby writes these vault records to its own vault segments and replace them to update its data files, maintaining consistency with the primary. Synchronization is tracked using log sequence number, which marks the exact byte position in the wall, so both end knows how far replication has progressed. Because replication happens at the block level and not as SQL statements, it is extremely efficient. Effectively a binary stream of changes that goes through, right? The results are near real-time synchronization with minimal overhead and fast failover capability. For more granular or cross-version setups, Postgres also supports logical replication. This is a variation of streaming replication, which essentially decodes the wall into logical changes. This enables selective table level replication by setting up a flexible publisher-subscriber model. Right? It can even be used for replicating data between different major versions of Postgres. Now, I did not put up another slide in the interest of time, but they are architecturally similar, but with the added ability to define a push-pull mechanism. How is this different in MariaDB, right? MariaDB uses a binary log or bin log based replication where all committed transactions on the primary are sequentially recorded in the binary log files. Each event in the bin log represents a logical change rather than raw data blocks. So when a transaction commits, as depicted in step 3, the changes are first flushed to the redo log buffer. To the redo log files. At the same time, the transaction events are also recorded in the binary logs. This serves as the source of replication and point-in-time recovery in MariaDB. A replica server connects to the primary and continuously fetches these bin log events. You could have one or more replicas. These events are then stored locally as relay logs and then replayed, right? Applying the same changes to the replicas data files. MariaDB also uses a global transaction ID to uniquely identify each transaction across all servers. GTID simplify, failover recovery and multi-source replication, by tracking the exact replication positions on each server. Replication can also operate in different modes. I've not made a note of that in the chart here, but it can be a statement-based, row-based, or a mixed mode. It also supports replication filters for tables or schema-level controls, similar to Postgres's selective table replication functionality. Another noteworthy point is Postgres replication is a primary standby model, whereas a MariaDB is a scale-out model, right, of a primary and a replica with async or semi-sync replication. For synchronous replication and high availability solution, Galera is the recommended architecture, which we will go through in the next slide. Now, MariaDB's Galera cluster is a true active-active multi-master solution. Every node is equal, and each can handle both reads and writes. Transactions are replicated in real time across the cluster, ensuring strong consistency and no data drift. It's built directly into MariaDB and tightly integrated into the InnoDB storage engine, so it doesn't work with any of the other engines. Galera uses a concept known as write-set replication, which captures the actual changes made by a transaction and certifies them across all nodes before commit. Replication events are ordered globally. Specifically, they are applied to all instances in the same order. This ensures that there's a synchronous consistency without using the binary log, unlike the traditional replication that MariaDB does. Under the hood, the write-set API hooks into MariaDB to enable replication. The Galera plugin handles the replication logic, and the GCOM, or the group communications layer, manages synchronized group communications between the nodes. And the best part is it is remarkably easy to set up. With a few configuration lines, you can deploy a fully synchronous multi-master cluster that scales reads and writes while delivering built-in high availability. This slide is a quick summary comparisons and how the replication differs between PostgreSQL and MariaDB. It's certainly not exhaustive. PostgreSQL's streaming replication, like I said, is physical, WAL and LSN based, and ideal for high availability. It uses open source tools like Patroni for failover. It also supports logical replication using a publisher-subscriber model. MariaDB's binlog replication is logical, replicating SQL changes. It is flexible for scaling out and version upgrades. It uses global ID transaction IDs for recovery and can be managed through max scale. Galera cluster takes it a bit further. This is a true multi-master and a high availability solution with all nodes being writable. And transactions are certified across nodes for a strong consistency. PostgreSQL's BDR extension aimed for a similar multi-master capability through logical replication and conflict resolution. It has since then evolved into a commercial raft-based distributed system supporting quorum and multi-write replication. I do not cover it in the discussion today due to its nature and complexity. But do note that there are various vendors who provide products to support this capability. So that's all I had to say on this topic. Hoped it helped paint a picture of the nuances of this critical feature that most applications rely on. We'll switch gears a little bit and talk about another key difference between MariaDB and Postgres, right? And that lies in how they handle connections. Now, essentially, how each client talks to the database. Postgres, as you know, uses a process-based model. So this means that every client connection spawns a new operating system process. It's simple, stable, and fault tolerant, but it comes with its overheads, as we know. Hence, Postgres often depends on connection pooling to efficiently manage large workloads, right? So you would have to factor in that as part of your database architecture as well. MariaDB, in contrast, is thread-based. All client connections run as threads within a single process. This allows for efficient handling of high concurrency. It's lighter, faster, and scales well. Like with threaded architecture, all threads share the same memory space. And depending on your school of thought, you could argue about the merits and demerits of one versus the other. Let's look at connection pooling, load balancing, and database proxy, given the background of how these database is architected. PostgreSQL uses a per connection process model, so connection pooling becomes essential for scaling and performance. PG Bouncer is one popular solution, providing a lightweight pooling layer. Effectively, reusing connections to minimize overheads, but it's just limited to pooling only. For more advanced capabilities, PGPool 2 adds load balancing, automatic failover, and query routing. Directing writes to primaries and read to replicas and so on. However, PGPool isn't ideal for pure pooling since it maps each client directly to the backend process and does not provide multiplexing capabilities like PG Bouncer does. It's also generally not preferred as the product has reliability and stability issues on in a production scale deployment. Together, PG Bouncer and PG Pool forms PostgreSQL's open source proxy options. Both are supported by the community. Additionally, Patroni and Rep Manager are open source tools that also provide HA failover management. Commercial failover and connection managers are also available in the marketplace that may address some of the other use cases that may be needed. So what's available in MariaDB in this space, right? MaxScale has been quite popular, and this is MariaDB's advanced intelligent database proxy that we provide. It is the crucial architectural component that allows MariaDB to offer seamless scaling, robust failover, and advanced security services. It acts as a smart SQL-aware proxy designed to manage high availability, load balancing, and read-write splitting. It helps you completely abstract the backend complexity from the application layer. It performs something known as canonicalization to identify query patterns. It uses an LRU-based cache to classify and route queries instantly. If a query has been seen before, MaxScale knows whether it's a read or a write query, so it's able to route them at wire speed. Beyond routing, MaxScale also delivers, automatic failover, transaction replay, query throttling to maintain, smooth operations under heavy loads. It can also act as a smart proxy with SQL firewalling, bin log streaming, and also has a browser-based management capability. Importantly, MariaDB or MaxScale transitioned from a BSL plus a GPL-based license, which was the case up till version 24.08, to a commercial license from version 25 onwards. This is in alignment with MariaDB's enterprise product strategy. In short, MaxScale doesn't just route traffic. It understands, optimizes, and protects every query that passes through it. All right. In summary, Postgres provides multiple tools that caters for specific needs supported by the open source community. On the MariaDB side, MaxScale is the all-encompassing enterprise-grade tool that provides a number of features critical for database systems. The latest version of MaxScale is available as a commercial license, unlike the older versions of it. Finally, we will wrap up by understanding the licensing ecosystem for the database engine itself. MariaDB uses the GPL version 2, which centralizes MariaDB's upstream, while Postgres's BSD license is permissive, and it enables broader independent commercial usage. The difference shows in the support models that is provided. MariaDB development is guided by the MariaDB PLC and the foundation, and we provide a clear centralized roadmap together with the users, customers, and community, and offering direct SLA-based technical support. In contrast, PostgreSQL project is community-driven, with the development and upstream code provided by the core community. Consequently, service-level objectives for support and fixes for PostgreSQL are distributed across several different providers. It's a choice, right, between a MariaDB centralized accountability and PostgreSQL's decentralized support. So that's all I had to offer today to compare and contrast the two databases. There were a few other topics also that I wanted to add, but with just this content, right, I had enough to cover in the 1 hour that we were supposed to talk, right? Let me just quickly switch and see if if there are anything in the chat that I need to talk to. Does MariaDB require any kind of connection pooling? By default, it's not required. The database is able to handle a high amount of connection that can support most enterprise workloads. Why adding more and more replicas in PostgreSQL can clog the primary as opposed to MariaDB? I'm not sure if I made a statement to that effect. Adding more and more replicas in PostgreSQL, it may not necessarily clog the primary, because once the transactions are written to the vault segments, it's the vault segments that publish it out. Depending on the synchronous mode that you're operating in, it may wait for the transaction acknowledgement from different primaries, right? And so that's a trade-off that you may have to do in your architecture and design. Row-based replications are not logical. That's a valid point, Alexander. Sylvian, the point was with Galera, you could achieve a synchronous replica. So if a customer was looking for having a near real-time failover, Galera would be the solution to go to, right? Because it will have transactions at real time. That's right. MariaDB provides both. Assuming maintenance, is MariaDB assuming maintenance development of MySQL community away from Oracle? No, I don't think so. And the question is MariaDB assuming maintenance development of MySQL community away from Oracle? And I don't think that the answer should be no, but I'll refrain from confirming or refrain from answering that question. Yeah, thanks, Roger. Thanks, Sylvian, for clarifying that. Yeah. All right. That is good. Thank you, folks. I hope that you found this session helpful, and you're able to use this, when you make your architectural decision on which database that you need to use. Thank you very much.
The MariaDB Foundation is the global contact point for collaboration on MariaDB server. Our work is made possible thanks to the support of our sponsors.